Hi, everyone. Welcome. It's the last week of lecture. Pretty exciting. You made it, despite uh, despite all the things going on currently. I hope you're well. I hope friends and family are still well. Yeah, it is the last week of lecture delivery. The Monday and Tuesday, the first week of May, I would like to offer a review session, which we'll do live, synchronously during class time. So anyone who is interested in a review session, show up, ask me to go over things, ask specific questions, for example, from the study guide that I'll be posting later this week. That'll happen during class time, either Monday morning or Tuesday afternoon, depending. Well, I guess Tuesday morning, 11 o'clock, depending when we would normally have class. Look also for more information about how the final exam will look, how it will be administered in the coming days, and look also for the last few grades that I have to posted and caught up, and yeah, that's the story. Don't forget that we do have a few mastering physics assignments due on Sunday. I encourage you to start early. Don't leave it all till the weekend. And let's see, this week we have a slightly nicer week. We've got a worksheet, I think, a recitation, and that might be it. Our calorimetry lab is due, the report for that is due the end of this week. And there is no lab experiment this week. So we're definitely coming to the end of things. Okay. Let's dig in. We left off having just started chapter 19, although there really isn't a whole lot left in chapter 19. It's, I think, the shortest chapter of the four. There's one or two pieces that we still have to catch up on, and then we'll head right into chapter 20 and finish things up. I'll start reintroducing the first law of thermodynamics. Yeah. That's how we wrote it last week. And it's worth mentioning the sign conventions for these different things. Q represents heat transfer. the transfer of energy via heating. And it could be positive or negative depending which way we were looking. This is all with respect to a thermal system. And once we agree on what the system is, if heat is flowing into the system, then Q is positive. If heat is flowing out of a system, then Q should be negative. If the system is doing work, let's say it this way. So delta U, remember, just has to do with the temperature. 3/2 NK delta T. And Boltzmann's constant, right? K sub B. The work, so the delta T handles the sign of delta U. In other words, we don't need to worry about that. If the system's temperature changes, then okay, its internal energy is going to change. The work done, if it's work done by a system, if the system is doing work on something else, doing work, the work is done by the system itself, then our convention is that we'll let W be positive. If it's work that we are doing on the system, upon the system, if we're compressing it manually by pushing on it, that's something we're doing from outside onto the system. And in the first law of thermodynamics, the work done by the system is opposite the work that we did. So if we're doing positive work, then the system is doing negative work. That is a pretty good reminder of how things went last week. Let me share my screen. We'll talk about some slides and we'll go from there. Okay. Chapter 19. If we are going to have to care whether it's heat transferring into or out of the system, the image of popcorn here is to remind us that we should be careful when we define what is and what isn't the system. Do you mean just the popcorn? Do you mean the popcorn and the pot and the lid? And what we're talking about is the heat transferring in from the burner underneath. It's okay either way. We just need to, agree with ourselves and be consistent with what is our system, what is external to the system, where is the heat transfer occurring. Some figures from our textbook to underscore what we wrote on the board a second ago. Heat is positive when it's going into the system. Work is positive when it's done by the system. Negative when it's done on the system. Heat is negative if it is transferring out of the system. When the volume is expanding, if the piston's moving away, suppose we do not transfer any heat. So I think if Q is 0, then delta U and W have to be equal magnitude and opposite sign. If the piston moves to the right, then it's due to the collisions from the molecules pushing on it. Those collisions give a little bit of kinetic energy to the piston itself. So we're transferring energy out of the system by doing work on the piston. And that's how the internal energy of the gas inside is able to decrease without doing any temperature changing. And this next slide is just the reverse of that. If the piston's moving towards the system, we're decreasing the volume, then the system is doing negative work. And the negative of the negative work means that the delta U gets to be positive, and the internal energy of the gas, which, remember, is just the kinetic energy if it's an ideal gas, increases. Here's a slide to remind us about how we calculated the work done by a thermal system. The piston is moving under the influence of the pressure of that gas, I suppose, whatever fluid it is under that we're using here in our thermal system, and that fluid or that substance pushes on the piston, exerts pressure on that piston, which in turn exerts a force upon it, so it moves. If it undergoes a displacement, then we have work done. And we have the same figure from last week. If our system undergoes an expansion from state 1 to state 2, then the work done is the integral of the pressure as a function of volume, or the area under the PV curve. If it's a compression instead, then we're integrating from a greater to a lesser, and we'll end up with a negative sign. And figure C there is the example for an isobaric process. And the work done, if the pressure is constant, we can factor it outside the integral, and we end up with just P times delta V, which is, again, points out to us that the work done during a process from state 1 to state 2 depends how we get there. If we go through state 3 first, it's a relatively large work that's done by the system. If we go through state 4 first, it's a relatively small work. And if we go directly from state 1 to state 2, then it's some amount of work that's between the two. There's one more kind of process that we didn't quite talk about last week. We talked about isobaric, isochoric, isothermal, and adiabatic. There's one more kind of process that we're going to need to talk about later this week, later today. And that's a free expansion. In figure A, the system is doing work on the piston, and there is a temperature maintenance. We're adding heat from that hot plate that we're sitting on, maintaining the temperature at 300 Kelvin. The heat transferring in, if we're maintaining the temperature, cannot go to changing the internal energy. It has to go towards the system doing work, pushing the piston up. In a free expansion, figure B, suppose we have constrained the gas in the 2 liters at the bottom of this tank. Now there's no hot plate anymore, but if we were able to contrive that partition breaks, the gas will expand to fill the entire 5-liter volume. That expansion happens without the possibility of any heat transferring in to this system because of the insulation happens without doing any work. There's nothing to push on. There's nothing that undergoes a displacement. There's no access to an environment on which this gas can push. It just fills the space. And so think about the first law, if there's no heat transfer and if there's no work done, then delta U must be 0. And we have to conclude that the temperature of a gas undergoing a free expansion like this is constant. If it was 300 Kelvin to begin with, it's 300 Kelvin now. A figure to remind us of the association, the equality of transferring energy by doing work and transferring energy by doing heating directly. And that's all due to James Joule, for whom we named the unit. This is largely a review from last week. It's just it's part of the story here, so I figured I'd refresh us a little bit. And again, just some consequences of that of the first law of thermodynamics. If Q is positive, 150 joules that we're transferring into the system, and the system's doing 100 joules of work, then 50 joules of that heat must have gone to change the internal energy. And we could rearrange the first law to solve for delta U, Q minus W. Delta U, it turns out, is the state variable. Q and W depend on how we get there, but delta U does not. It only depends on the temperature for an ideal gas, in any case. If the heat flow is negative, that means it's flowing out of the system. And if we are doing 150 joules of work on the system, or if the system's doing negative 100 joules of work, then Q minus W means that we must have changed the internal energy by negative 50. If the heat transferred in and work done by the system are equal, then the internal energy cannot have changed. And that's figure C here is an example of figure A here. It's a heat transfer in, work done by the system, temperature change 0. In a process, a cycle where we return from one state to the same state, the amount of useful work that's done is the difference between the forward interval and the backward interval. If we follow the path from A to B, we've got this sort of pinkish area here of positive work. And then if we follow the upper arrow from B back to A, we would have an entire negative area of everything from that curve. Oops, I'm sorry. From that curve down to the axis. Some of it is canceled by the positive integral we had on the way through, and that cross-hatched area is the difference, which in this case is negative because we're walking backwards. We had a greater amount of negative work done by the system than positive work done by the system. Examples, a diagram showing the 4 kinds of process that we're interested in talking about. Free expansion, again, is another thing. It takes some setup, right? We've got to sort of trap the system and then allow it to expand into a vacuum, so we have to evacuate part of it. Suppose we've got a gas fully taking up whatever volume it's in. these are the four processes in which we are interested. Note that if you found the area under each of these four curves, they'd be different. The work done by an isobaric process from state A to state 3 is very, very different from the work done in an adiabatic process from state A to state 1. Note also that the final temperature in state 1 has to be less than the temperature in state A. These blue curves that go from the top left to the bottom right are curves of same temperature processes. Curves for which anywhere on that curve, PV over NR evaluates to the same temperature. So in order for an adiabatic process to have a steeper slope than an isothermal process, the only way to do that is for the temperature to actually change that way. This is the same figure again. I'm not sure why we had it twice. Okay. The shape, by the way, that's the function that represents the adiabatic curve, the adiabatic process from A to 1, and the isothermal process from A to 4. Those functions are part of the work that you did this week with this week's recitation, or I guess this last week's recitation, wherein you calculate the work done during each of these four processes. We can show that the slope of the adiabatic curve is steeper than the isotherm. If you are curious about that, let me know. We have two kinds of process that we're talking about. We've got an isochoric, same volume process, and an isobaric, same pressure process. And those two kinds of process have a different relationship between the heat added and the temperature change. It's at this point that I'd like to pause sharing the screen and do a little bit of work at the board to explore the consequences of that. All right. I'd like to keep the first law of thermodynamics in this form, solved for Q. Suppose we talk about a constant volume process, an isochoric process. Isochoric. In an isochoric process, the volume cannot change, which means the work done is also zero, because the integral from one value to the same value is zero. So that means that Q is just equal to delta U. Now, Q, back from chapter 17, we said was, we said it was M times the specific heat times the temperature change. In chapter 18, though, the internal energy of an ideal gas, we said, was 3/2 capital N K Boltzmann change in temperature. Okay. Remind me again. So N and K Boltzmann. N is the number of molecules. That was from our kinetic theory. But Boltzmann's constant we got to by taking the gas constant R and dividing by Avogadro's number. Okay, so let's put that back. 3/2 number of molecules R over N Avogadro delta T M, the mass of the sample, is the molar mass times the number of moles. You remember this. The molar mass times the number of moles. So there are 3 moles. Each mole has this much mass. That's the total mass of the sample. And we said that we were going to combine the molar mass and the specific heat, because those are both things that depend on which substance it is that we're talking about. We combine those into these molar heat capacity. N delta T equals 3/2. Now, the number of molecules divided by Avogadro's number. Well, okay. Suppose there are 12 times 10 to the 23rd molecules. If we divide by 6 times 10 to the 23rd, Avogadro's number, we'll end up with 2 because there are 2 moles. So capital N over Avogadro's number, that's just the number of moles. Huh, all right, cool. So wait, we've got an N on both sides, we've got a delta T on both sides, and we've now said that the molar heat capacity is 3/2 R for any ideal gas. Wow, that's pretty cool. Frankly, that's very cool. Or at least it's the molar heat capacity for a process that is isochoric. Just to be safe, I'm going to put a little V here. It's the molar heat capacity for any process in which the volume is constant. So this is molar heat capacity at constant volume. What if the volume weren't constant? Would the molar heat capacity be different? Let's find out. What if instead of an isochoric process, we considered, now I'd like to keep at least one thing constant. In an adiabatic process, remember the pressure and the volume are definitely changing, and the temperature changes as well. In an isochoric process, we kept the volume constant. In an isothermal process, we keep the temperature constant. But if the temperature is constant, then there's no delta T to talk about a heat capacity for. So the only other option, and if I don't really want to talk about an adiabatic process, I'd like to talk about what is isobaric. In an isobaric process, we've got some heat transferred in. The internal energy changes, and we get some amount of work done. And since it's isobaric, the integral of P dV, the pressure we can pull outside the integral because it is isobaric, and we're just talking about the pressure times the change in volume. You know what? I don't want to accidentally integrate one term when we should have integrated more terms. Let's talk about it this way. Let's talk about a small amount of heat coming into the system, a small change in the internal energy, and a small amount of work done. A differential work, that's the integrand of the work formula. That's P dV. When we integrate, we'll make that same choice that we just made. Small amount of heat is related to the, well, it's mc dt, or it's related to n capital C dt. The small change in the internal energy is related to 3/2 nr dt, and that's just from before. It used to say capital NK, but in a few minutes ago we rewrote it so that nr is equal to nk plus p dv. Now, if this is an ideal gas undergoing an isobaric process, then the pressure, let's see, PV equals nRT. If we're keeping the pressure constant and we're keeping the number of moles and the gas constant, we take a derivative of both sides. We're talking P dV here is nR dt here. So this P dV is nR dt. There's a dt in every term. There's an n in every term. So now we're starting to say the molar heat capacity 3/2 n plus, oh, I'm sorry, 3/2 r plus r, which is 5/2 r. This is not the same result. This is a different heat capacity. The heat capacity we had before was 3/2 r. This was C sub V, the molar heat capacity at constant volume, plus R gets us a different kind of heat capacity at constant pressure, isobaric. At constant pressure, we're allowing the system to do work. So the energy that we're transferring into the system by heating could go, like, it has options, right? It could go to change the temperature, or it could go to change the work, or to do work. For an isochoric, a constant volume process, there's no other option. Every Q that we put in has to change the internal energy. It can't be done. Every Q changes the temperature. For an isobaric process, we can spread it around. Some of the energy goes, some of the heating goes to changing the temperature. Some of it goes to doing work. So the heat capacity, the storage, right? We're able to transfer in more heat and end up with the same temperature change, because some of the heat that we transferred in went to doing work instead of changing the temperature. So I think it makes sense that the storage capacity is a little bit bigger, because then now we're allowing there to be something else that we do with the heat that we're transferring in. Okay, cool. So, I mean, the two heat capacities are really just multiples of each other, or like they're really closely related. They're both in terms of the gas constant, R. So that makes me think there's a nutshell here that, well, okay, so let's C sub V is 3 halves R. C sub P is 5 halves R. And the ratio between them so that's 5 halves R to 3 halves R. The R's cancel, the over 2's cancel, and we're just left with 5 over 3, 1.67. Let's call that gamma. Gamma is this weird sort of symbol that looks sort of like that. It's like an R or a V or something like that. I usually draw mine with a little loop so that I know that it's not an R or a V. Okay. This is interesting. So, and this is true for any ideal gas. That's pretty cool. Any gas that meets our conditions, the assumptions that we made for the kinetic model, which is point particles that don't interact. Okay, cool. Let me go back to the slides for a second. Monatomic gases, point particles that don't interact. Helium and argon are really good examples of this. The noble gases, very inert. Helium's molar heat capacity at constant volume is 12.47, and just for laughs, imagine calculating 3 halves of 8.314. Yeah, it's 12.47. The molar heat capacity at constant pressure is 20.78, which is almost exactly what you'd get if you calculated 5 halves of 8.314. The difference between them is a single R because, well, yeah, that's how we derived it. And gamma is, in fact, 1.67. Experimentally, not theoretically like ours was. Now, the the diatomic gases here have completely different numbers. The molar heat capacity at constant volume is 20. And the at constant pressure is 29, 28 or so. The difference between them, interestingly, is still 8.31, is still R. And the gamma is essentially still the same value within the group of diatomic molecules here. You know, they're all basically 1.4. But why are there, you know, why are the molar heat capacities different for diatomic gases than for monatomic gases? And, you know, gosh, never mind what happens to the polyatomic gases. They're all over the place. Well, although gamma turns out to be really close to 1.3 for the polyatomic, even though their heat capacities are all over the place. That's really interesting. Let's try to explain that. Explaining that means that I need to go get a different set of slides. So I'll stop the segment here and we'll pick up here in a second.